Welcome to Talk Tensors, where we dig into the latest, really impactful research in machine learning.
Glad to be here.
So today we're tackling something pretty significant. How do we actually use these incredibly powerful, but also, computationally hungry multimodal models?
Yeah.
The ones that handle images and text.
Yeah, in the real world, right? Where you don't always have unlimited computing power.
Exactly. And the paper we're diving into, Learning to Inference Adaptively for Multimodal Large Language Models, offers a really interesting solution.
It does. I mean, these MLLMs like LLaVA, they're amazing at visual reasoning, no doubt.
But they need serious hardware.
Totally. Running them outside of big data centers is tough.
Yeah.
And even there, efficiency is a huge deal.
Right. And the usual way is to make them faster or smaller. They kind of lock you into one specific speed versus accuracy setting.
Exactly. It's a fixed trade-off. What this paper proposes at Adolava is different. It's about letting the model adjust its own computational load while it's running.
Adapting on the fly.
Yeah, adapting based on what you feed it, the image and the text, and also based on how much time or power you actually have available right then.
Okay, so it's not about building a permanently smaller, maybe dumber model.
No, not at all. It's about taking a top-tier MLLM and making it smart enough to decide, okay, for this specific task, how much effort do I really need to put in?
Like a skilled chef, you mentioned before we started recording, adjusting based on ingredients and time.
Precisely that analogy. The author suggests we think of a big MLLM as like a collection of shallower networks all nested together, sharing the same core knowledge.
So like layers of understanding.
Kind of. Imagine those transformer blocks, the building blocks of these models, stacked up. For a simple question, maybe you only need the first few layers.
But for something complex, you use the whole stack.
Exactly. And Adolava introduces this learned scheduler. That's the really novel part.
A scheduler. Okay, so it's like a manager inside the AI.
You could think of it that way. It generates an execution plan. It decides which specific bits inside the MLLM, maybe skip a whole block, maybe turn off some attention heads, should be active for this input, given this time limit.
Wow, okay. An AI managing another AI's workload to hit a deadline.
Pretty much. And it's trained to do this intelligently. The goal is always to get the most accurate answer possible without going over the specified latency budget.
And they tested this thoroughly.
Oh, yeah. Across standard benchmarks, question answering, reasoning, even checking for hallucinations, making stuff up.
Right.
And the results look good. Adolava seems to really handle that accuracy-latency trade-off dynamically.
Okay, let's get into the paper itself then. How did the authors frame the problem and their contribution?
Well, they start, laying out the issue clearly. MLLMs are powerful but expensive. Existing efficiency tricks give you a fixed result, this much speed for this much accuracy, take it or leave it.
Which isn't ideal for the real world.
Not at all. Real-world deployment, whether it's busy servers or like an edge device, needs flexibility. Sometimes you need a fast answer, sometimes accuracy is paramount, and resources fluctuate.
So Adolava is pitched as the answer to that need for flexibility.
Right. They call it latency-aware adaptive inference. And the key insight, as we said, is viewing the MLLM as this collection of potentially shallower models.
And that bypassing parts like transformer blocks or attention heads can save time without completely wrecking performance.
Exactly. If you choose which parts to bypass strategically, you can create different versions of the model on the fly, all sharing parameters, but having different speed accuracy profiles.
Makes sense. And then after setting the stage, they talk about related work. How does Adolava fit in?
Yeah, they cover the background well. They talk about the history of adaptive inference, generally early stuff on feature selection, then more recent work on deep models like CNNs and VITs where people tried skipping layers or patches.
So adapting computation isn't totally new.
No, but they position Adolava as specifically targeting MLLMs, focusing on latency as the driving constraint, and making decisions based on both the input and that variable budget.
And they also mentioned other ways people make MLMs efficient.
Right. Things like building smaller models from scratch, like Phi2 or TinyLaVA, using tricks like mixture of experts or pruning input tokens.
Okay.
And they make a point that Adolava is kind of orthogonal. It works with an existing model and can actually be combined with some of those other methods, like token pruning, for even bigger gains.
Interesting. So it's not an either-or situation.
Potentially not, yeah.
Okay, let's get into the mechanics then. The scheduler. How does it actually work? How does it reconfigure the MLLM?
So the core job of the scheduler is, given the image, the query, and a latency budget, like, say, max FLOPs or milliseconds, it figures out which parts of the MLLM to run.
To meet the budget but keep accuracy high.
Exactly. They first lay out the standard MLLM setup image, gets turned into visual tokens, text into text tokens, they get combined, fed to the LLM, answer comes out. Standard stuff. Then they introduce these switches. Think of them as K-binary switches, basically on-off toggles attached to different operations in the LLM part, like a whole transformer block, or maybe just some attention heads inside a block.
K switches, so K potential points of control.
Right. And the scheduler's job, defined by its own parameters, let's call them phi, is to look at the input tokens and the latency budget and output a configuration S for all those K switches.
Okay, so S is the execution plan.
Yep. And the overall goal is to find the ES that minimizes the model's prediction error, subject to the constraint that the latency of executing plan ES is less than or equal to L.
That sounds complicated to optimize directly during training.
It is. They mention that trying to solve that constraint optimization directly is too expensive.
So what did they try first? You mentioned they had an initial approach that didn't quite work.
Yeah, their first pass was deterministic. The scheduler would just predict a hard 0 or 1 for each switch on or off.
Straightforward.
Seems like it, but during training, they just added a penalty if the predicted plan went over budget. They found empirically that this didn't reliably enforce the budget. Sometimes it still went over. And maybe more importantly, it often produced kind of suboptimal plans, like maybe it turned off too much stuff even when it had budget left over, didn't use the resources well.
Okay, so the deterministic approach was flawed. What was the fix?
They moved to a probabilistic model. Instead of predicting a definite on-off, the scheduler learns to output a probability distribution over the possible switch configurations.
A distribution?
Oh.
Okay, how did that help?
Well, the idea is the scheduler learns how likely each possible plan is to be good for a given input and budget. Crucially, during training, they sample an execution plan's ES from this distribution, but they do it in a way that guarantees the sampled plan meets the latency budget.
So the budget constraint is handled during the sampling.
Exactly. Then they calculate the model's prediction loss using that sampled valid plans.
But how do you backpropagate through sampling? That's usually tricky.
Right. They use a standard trick for this, the Gumbel softmax approximation. It lets them get gradients flowing back to the scheduler's parameters, even though there was a sampling step involved.
Clever. Okay, so that's training. What about when you actually want to use the model? During inference?
During inference, they simplify. They just ask the scheduler for the most probable execution plan according to the distribution it learned, the one that fits the budget, and run that plan.
Got it. So probabilistic training enables deterministic but adaptive inference.
Pretty much, yeah.
Now, these switches, where exactly did they put them? You mentioned layers or heads.
They tried two main setups. First is Adolava for layer level. Here, each switch controls an entire transformer block. If the switch is off, the block is just skipped using a residual connection, a shortcut.
Okay, coarse-grained control.
Right. Then there's Adolava H for head neuron level. This is finer grained. Switches inside the blocks control individual attention heads or groups of neurons in the feed-forward parts.
So you can be more selective within a block.
Exactly. And they were careful to make the scheduler itself lightweight so it doesn't add much overhead. They actually reused the first few LLM blocks to process the input and the latency budget information.
How does the latency budget get fed in?
It's encoded into a special token embedding. They use sinusoidal position encoding plus a small MLP and just append it to the input sequence. That token attends to everything else in the early layers.
Neat trick.
Then the representation of that latency token, after processing, goes into a simple linear layer that outputs the probabilities for the switches.
Makes sense. And they measured latency in terms of FLOPs.
Yeah, they used FLOPs as the proxy for latency budget, focusing on the prefill stage, which is often the bottleneck. And usually they applied switches only to the latter half of the LLM layers.
Okay, let's talk results. Did it work? Did it stick to the budgets?
Yes, the results in the paper look pretty strong. They built Adolava on LLaVA 1.5 using both 7B and 13B parameter models and tested zero-shot on benchmarks like BQAB2, ScienceQA, MME, POPI, etc.
Standard multimodal tests.
Right. And the main finding is that Adolava, especially the finer-grained Adolava H, could get performance very close to the original LLaVA 1.5 when given the full budget.
Okay, no loss at 100% budget is good.
And then when they cut the budget, say, down to 85% or even 60% of the original FLOPs, the accuracy drop was quite minimal. We're talking like 1-2% drop at 85% budget for Adolava H, maybe 3-4% at 60%. Sometimes even slightly better on specific tasks at lower budgets, interestingly.
Wow, that's a pretty graceful degradation.
Yeah.
And it did hit the budget targets.
Yes. They emphasize that due to the probabilistic sampling strategy during training, it consistently adheres to the specified latency budget, no violations.
That's crucial. And what about combining it with other methods like token pruning?
They showed that too. They integrated Adolava with token selection methods like PruMerge Plus and FastV.
And synergy.
Yep. The table shows further efficiency gains. Adolava essentially lets these already pruned models also adapt to varying budgets.
You get the benefit of fewer tokens and adaptive computation.
Exactly. For instance, Adolava H combined with PruMerge Plus at an 85% budget relative to PruMerge Plus alone actually boosted accuracy slightly in some cases while still saving compute.
That's impressive. Beating the baseline while using less compute.
Yeah, it suggests Adolava complements these other techniques really well. They mention one combo reducing compute by like 70% compared to the original LLaVA 1.5 with only a tiny 1.7% accuracy drop.
Okay, really promising results. Did they do other analyses, ablations, or visualizations?
They did. They showed nice accuracy latency trade-off curves, Pareto frontiers, demonstrating how Adolava lets static models like LLaVA 1.5 or PruMerge Plus trace out that curve, adapting across budgets from 50% to 100%.
Visualizing the adaptability.
Right. And they looked at content adaptivity too. They showed that even with the same latency budget, the scheduler picks different execution plans activating different blocks depending on the specific image in question.
So it's not just the budget, it's also what it's being asked.
Exactly. They have figures showing attention maps from the latency token highlighting relevant image regions, and diagrams illustrating how different blocks get enabled or disabled for different inputs under the same 75% budget. It really seems to tailor the computation.
That's really cool. What else?
They showed it generalizes by applying a DAL-A to a different MLLM, MIFA3B, which is based on Phi2, and saw similar adaptive behavior.
Good sign. It's not just a LLaVA-specific trick.
Definitely. And critically, they did an ablation comparing their proposed probabilistic training to that initial deterministic idea.
And the probabilistic approach won out.
Clearly. The results showed the probabilistic model adapted much better across different budgets, whereas the deterministic one had bigger performance drops at low budgets and, as mentioned, sometimes violated the latency constraint. It really validated their design choice.
Okay, this all sounds like a really solid piece of engineering and research. To put it in context, how does this fit into the bigger picture, the history of making AI more efficient?
Well, it definitely connects to a long lineage of work. People have been trying to make neural nets cheaper to run for ages. Early ideas like conditional computation only run parts of the net if needed, or dynamic networks that could change structure.
Right.
But a lot of early work was maybe less dynamic at runtime, or focused on single modalities. Adolava's strength is this runtime adaptation specifically for complex multimodal models, driven directly by both the input and an explicit varying latency budget.
And the need for this is just growing.
Right, absolutely. We want to put AI everywhere. Phones, cars, sensors, web services with fluctuating loads. Static efficiency isn't enough anymore. You need models that can cope with resource constraints that change moment to moment. And MLLMs processing images and text are inherently complex, making adaptive computation even more valuable.
So boiling down, what are the clear, non-repetitive takeaways here?
Okay, first, Adolava gives us a practical way to deploy these powerful MLLMs where resources aren't guaranteed or latency needs vary.
Makes them more usable in the real world.
Second, the learned scheduler is the key piece of magic, making intelligent choices about what parts of the model to run.
The AI manager.
Third, the probabilistic training is crucial for actually meeting the latency budgets reliably, no guesswork.
Reliability is key for deployment.
Fourth, it's flexible. It can potentially be combined with other efficiency techniques, like token pruning for compounded benefits.
Stackable improvements.
And fifth, it's not just adapting to the clock, it's adapting to the content. It changes its strategy based on the image and text it sees.
Content-aware adaptation. That's really sophisticated. Okay, thinking about the real world then, paint us a picture. Where could this actually make a difference?
Imagine your phone. An MLLM running on it using a diverter could automatically dial back its computation when your battery's low, or if you start running a demanding game. It stays useful, just maybe a bit less responsive temporarily.
Instead of just crashing or draining the battery.
Right. Or think about cloud services. Companies running MLMs could use Adolava to handle peak loads more gracefully. maybe slightly reducing computation per query, instead of needing massive over-provisioning, saving potentially millions in hardware and energy costs.
Economic impact.
Definitely. Or for something like a virtual assistant, maybe you usually want a super fast response. You set a tight budget. But if you ask a really complex research question, the system could recognize that and maybe implicitly allow a slightly higher budget for a more thorough answer.
User experience tuning.
And just broadly, making these models lighter and faster makes them more accessible. More people on more devices could benefit from this kind of AI.
Yeah, democratization of powerful AI. Okay, this has been a fantastic breakdown. To wrap up our main discussion on Adolava, what's the final summary?
Adolava introduces a really novel and effective framework for adaptive inference in MLLMs. Its core strength is using that learn scheduler, trained probabilistically, to dynamically configure the model's execution based on both the input content and a specified latency budget.
Achieving those accuracy-latency trade-offs on the fly.
Exactly. It shows content awareness, integrates well with other methods, and importantly, sticks to its latency promises. It's a significant step towards making these advanced models truly practical for diverse, real-world applications.
Definitely feels like a key enabling technology. All right, now for our novel notions segment. Taking the core idea of Adolava dynamic, adaptive computation, where could this lead next? What's a more speculative, maybe slightly out there extension?
Okay, so Adolava adapts which operations run within a fixed architecture. What if we push that further? Imagine models that could adapt their actual architecture over time, not just during a single inference run.
Whoa, okay. Not just skipping blocks, but actually changing the blueprint. How would that work?
Yeah, think a continuous architectural adaptation. Maybe the model observes, hey, this set of attention heads hasn't been very useful lately for the tasks I'm seeing, and it prunes them. Or conversely, I'm consistently hitting performance limits on this type of reasoning. Maybe I need to allocate resources to grow a specialized module here.
So the model itself learns to restructure based on experience.
Kind of. It wouldn't just be adapting to a single query and budget like Adolava, but evolving its structure based on longer-term performance trends, data distributions it encounters, resource availability in its environment, like lifelong architectural learning.
That sounds incredibly complex. What kind of feedback would drive that?
It would have to be multifaceted. You'd have the usual suspects: accuracy, latency, maybe energy consumption. But you could also imagine feedback from, say, gradient flow analysis during any ongoing fine-tuning, statistical properties of the input data streams, maybe even some form of direct reinforcement learning based on task success or user feedback about resource usage.
Almost like a fleet of these models deployed in different places could learn collectively.
Potentially. Different instances facing different challenges could evolve slightly different architectures optimized for their specific niche. Maybe one running on a server farm evolves differently than one on a mobile device. It's moving towards models that don't just learn knowledge, but learn how to structure themselves optimally over time.
What makes this feel like a logical, if distant, next step from Adolava?
Well, Adolava introduces the principle of runtime computational adaptation based on learned signals. This novel notion just extends that principle from selecting operations within a fixed structure to potentially modifying the structure itself. We already have things like neural architecture search, but that's typically a separate offline phase. This imagines making architectural adaptation an online, continuous process integrated with the model's operational life.
The challenges must be immense, though. Stability. Ensuring it doesn't just break itself.
Oh, absolutely. Monumental challenges. Ensuring stability, preventing catastrophic forgetting or destructive modifications, managing the computational overhead of the adaptation process itself. It's definitely speculative research territory. But the potential payoff, truly self-optimizing AI systems that adapt their fundamental structure to their environment and tasks, is a really compelling long-term vision inspired by the kind of adaptive thinking Adolava represents.
A fascinating, if mind-bending, possibility. Well, for listeners wanting to explore the here and now of adaptive inference, the link to the LLaVA paper is available in the description. This was a great deep dive.
Really enjoyed it. It's exciting work.
Thanks for joining us on Talk Tensors. We'll catch you next time for another exploration into the cutting edge of machine learning.